Okay, guys, so let's start. So we're going to start with chapter 3. We're going to look at formula mass and the mole concept. So this is going to 3.1 is going to kind of launch us into eventually reactions in stoichiometry, and that's kind of the meat of unit 2, which is looking at changing matter into different things, but keeping track of where they are. So let's start with this covalent compound here. So this is a ball and stick representation of a covalent compound. We do not use ball and stick all that often, but when we do, we always use the same colors to represent different molecules. And we're going to end up talking about these three-dimensional shapes and all that. But right now, what I want you to recognize is each of these little spheres represents a different element. And we often use black to represent carbon. These small little white balls are used to represent hydrogen. And then finally, these larger spheres to represent everything else. Now, it's a covalent compound because it's a covalent compound because it's all nonmetals. And green is used to represent chlorine. Red is used to represent oxygen. Blue, light blue, is used to represent nitrogen. I think purple is for iodine. Brown is for bromine. So every single non-metal typically has its own color. Yellow is for sulfur, so they all have their own color. But nonetheless, we have a compound, a covalent compound here. I know it's covalent because it has all non-metals in it. Now, we never represent it like this, but this is what they look like. So from this, what we want to do is we want to be able to pull an actual structure out of it. So we always count the number of carbons first. This just has one carbon. The second thing we write are the number of hydrogens. This only has one. And then finally, Cl3, because there are 3 chlorines. And if we had more than one, we'd always put them in alphabetical order after the hydrogen. So number of carbons, number of hydrogens, and then alphabetically everything else that's attached. Okay, so this is our compound, CHCl3. Well, if we want to know the mass of this formula, what we're going to look at is, well, what are the mass of the individual parts? I have 1 carbon. I have 1 hydrogen. I have 1 chlorine. Or I'm sorry, I have 3 chlorines. So if we add those up all together, we're going to get our compound out. Now, we know the masses of these things because we have a periodic table. So on average, a carbon is going to weigh 12.01. So 1 times 12.01 AMU, atomic mass units. It's the average of protons and neutrons with all of the natural abundance included. So carbon weighs 12.01. I have 1 hydrogen, which is 1.008 AMU. And then we have 3 chlorines. The 3 chlorines are 35.453, but 35.45 is what I'm going to use. I'm going to use the periodic table that I provided for you. It's in the important info in your modules. I'm just going to use that so there's consistency throughout all my lectures. We're using the same periodic table. All right, so I'm going to add these all together. So first, I'm going to multiply out that 3 times 35.453, and we get a total of 106.35 AMU. So now I'm just going to add the other parts to it. So 106.35 for the chlorine, plus the 1.008 for the hydrogen, plus the 12.01, plus the 12.01 for the carbon, gives me a grand total of 119.368 AMU. So I think I freaked you guys out a little bit with the significant figures. So let me just simplify it. For this, I'm not too worried about sig figs. We could leave it as 119.368. If we wanted to follow sig figs, we would round to the second number here. So 119.37 AMU. But I'm not going to worry about the precision so much for formula masses and stuff, as long as you don't go out to like 40 decimal places or something. Okay, so 119.37 AMU. That is the mass of a covalent compound. Fantastic. So that's where we start. Pretty straightforward in terms of the atomic mass. We're adding up all of the parts. we know how much is in here. So this is the formula mass of one of these compounds. Now, my question to you, what is the formula mass of sucrose? So we have this mess here. And the reason that I'm talking about this stuff now is because I want to get you guys used to these crazy looking line structures, which once we're good at it, you're going to have no problem with it. So first and foremost, I want to point out the fact that there are a bunch of crazy looking scary wedges, like this wedge right here, and this little dashed line. All three of these are the exact same. They're just a bond, okay? So we're not really going to have to worry about those other than saying, hey, those are just bonds, don't worry about them. They are going to count the exact same. So because all of organic chemistry is based on carbon, we typically don't represent carbon with the symbol. We don't represent it with C most of the time. So for example, when I go from this OH group up here and I change directions, there is a carbon right on that corner. So whenever we change directions in one of these, there is a carbon present. So there's a carbon here. There's a carbon here. There's a carbon here, 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 here. We write in the ones that that are not carbon. So oxygen, there's a carbon here, 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 and here, I think too. So we don't typically write in carbons because it would look pretty messy if I put carbon at each of these locations, right? And then it's just a pain in the butt to do. It's much easier as a chemist to draw these line structures because other chemists can read them. The other thing we do is we don't add hydrogens on the carbons either. So what we know is each carbon is going to have 4 bonds. So if a carbon has 4 bonds, any missing bonds are going to be hydrogens, bonded hydrogens. So this carbon right here, how many bonds does it have? 2 bonds. If it has 2 bonds, the remaining 2 will be hydrogens attached to it, okay? And so we're going to do that for all of these. Carbon, how many bonds does it have? It currently has 1, 2, 3, so it's missing 1. We're going to add a hydrogen here as well. So every single one of these hydrogen or carbons needs hydrogens added until it gets to 4, okay? So pause me and do the rest because I'm going to do the rest right now, but here we go. So 3 bonds there, 1 hydrogen there, 1 hydrogen there. And right now, it doesn't really matter where you put them. It will in the future, but for now, we're just going to put them where we find space. Here, it doesn't need any because it's already got the 4 bonds. 1, 2, 3, 4. We're good to go. It's got its 4. We don't need to add anything. This one needs a hydrogen. This one needs a hydrogen. 1 here and 2 here. Okay, great. So we have labeled this thing. And so now I want you to count everything out and tell me what you have in terms of total carbons, hydrogens, and anything else. So how many carbons do we have? So we're going to count through them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I have 12 carbons. Count the number of hydrogens because that's next. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And I think that is it. So I have 22 hydrogens. And now last little bit, let's count the oxygens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 hydrogens or oxygens, 11 oxygens. Okay, so that is the start of our sucrose. So again, we counted them out, carbons first, hydrogen second, and everything alphabetically after that. So I have 11 times 12.01. Again, this is my carbons. Then I'm going to do hydrogens. I have 22. Oh, sorry, not 11. I have 12 carbons. 22 times 1.008 hydrogens. And then finally, I only have oxygen as the additional. So 11 times, keeping it consistent, 12's, let's see, 16, I'm guessing. Let's hit it. There we go. 16.0. By the way, on most periodic tables, oxygen's like 15.9994, so it's easy enough to do. All right, so there we go. And I think what we're probably going to do is we're going to do this and then add them together. So what do we got? So 12.1 times 12 gives me 144.12 AMU. Next, 22 times 1.08 gives me 22.176 AMU. And then finally, 11 times 16, 11 times 16, 176 AMU. So add them all up, 176 plus 22.176 plus 144.12 gives me a molar mass for sucrose, or this molecule, at 342.296 AMU. Good enough. We would probably truncate it after 2, but that'll work. Okay, so 142.296 atomic mass units. That is the mass of our sucrose molecule. All right, let's take a look at ionic compounds. So ionic compounds are slightly different. Ionic compounds are quite a bit different. It's hard to tell based on the structure how many are actually there, because if you look at this structure, you immediately say, well, the important part to pull out of here is like, oh, there are an equal number of purple to yellow, or to green, right? So the green ones are sodium plus, and the purple ones are chlorine. Oh, actually, I got that backwards, don't I? You know how I got that backwards? Because chlorines are always green. Chlorines. And we have sodium ions. So we have sodium and chlorine. It looks like we have an equal number. Unfortunately, we can't really know unless we do certain math, which we're going to do in the solids section much, much later in the semester. But I will tell you that we do, in fact, have NaCl as a compound. So what is the molar mass of sodium chloride? Okay, so we have one sodium at 22.99, and I have one chlorine at 35.453, both AMU. So I think it comes out to about 40. Let's see, 22.99 plus 35.45, 58, oh, way off, 58.44 AMU. There we go. So that's the molar mass of my ionic compound. What is the molar mass of cadmium nitrate? So give that one a go, and we'll go over in class. All right, Avogadro's number. So Avogadro's number is the representation of 1 mole. So we've been looking at atomic mass units, but the problem with atomic mass units is they're like individually sized. So we don't really care about the weight of one formula unit. I don't care about one sucrose molecule. I care about a large quantity of sucrose molecules. So Avogadro's number helps us take the molecular world and actually see it in a large scale. So it's important to recognize that this, again, is just a conversion factor. So 1 mole is equivalent to a quantity. It's not quite the same as a lot of the other conversion factors that we use. So 1 mole is equal to 6.02 times 10 to the 23rd objects. There's nothing associated with a mole other than that number. Just like 1 dozen is equal to 12 objects. Okay, if I told you to go get a dozen eggs, you would come back with 12. If I asked you to go get a mole of eggs, you'd come back with 6.02 times 10 to the 23rd objects. Okay, this number is massive, just to give you an idea. A 1 mole of, there are, I think the grains of sand on the grains of sand on the planet Earth don't even equal 6.02 times 10 to the 23rd grains of sand. Like, it is a massive number. Okay, so a mole is a very large quantity, but when you're dealing with something at the molecular level, it's actually not that much. So 1 mole of carbon atoms is 6.02 times 10 to the 23rd carbon atoms. Notice how carbon atoms. So what's changing is the quantity. So 1 mole represents this number, nothing more, nothing less. We're not trying to, that's it. Okay, so a mole is just a number. It's not, it's just a number to figure out how many things that we have here. In fact, we don't really use it all that often. We just have to understand the concept of it. So let's take a look at this first example, and then I'll let you guys do the rest. So how many molecules are there in 2.50 moles of C6H12O6? Okay, so I want to know, my original number is going to be 2.50 moles. And at this point, what we want to get used to doing is also writing the compound down, H12. I know it takes a little extra time, but it's going to be helpful in the future, especially when we get to stoichiometry in the next little bit. So 2.50 moles of C6H12O6, and I want to convert from moles into molecules. So I want to know how many individual molecules exist. So we're going to use moles because we do know that 1 mole of C6H12O6 is equal to 6.02 times 10 to the 23rd C6H12O6 molecules. Okay, so we can set that up as a conversion factor. I want moles of C6H12O6 on the bottom, and I want just simply the molecule on the top. So 1 mole is equivalent to 6.02 times 10 to the 23rd. And we do the math, and what you end up with is 1.505 times 10 to the 24 C6H12O6 molecules. Sorry, my writing got a little smushed. All right. Okay, sig figs. My measurement has 3 sig figs, so my answer should have 3 sig figs. So 1.51 times 10 to the 24th C6H12O6 molecules. There's my answer. Okay, easy enough. All right, how many moles of helium are in a sample that contains 3 times 10 to the 22nd atoms? And so now we're just going to do the opposite. We're going to go in a different order. So 3 times 10 to the 22nd atoms times equals, I want atoms on the bottom, and I want, or I guess helium atoms, and I want moles of helium on the top. So 1 mole of helium is equivalent to 6.02 times 10 to the 23rd. That's a 3. Here we go. And we do the math. Again, I didn't cancel before, but let me do it now. Moles cancels, and this one, helium atoms cancel, and I'm left with moles of helium. And we end up with, let's see, 0.05 moles. We use molar quantities because I'm going to show you in class like what 1 mole of aluminum is, or 1 mole of water, or 1 mole of sand, SiO2, not actual sand grains. But we use this because these numbers are more manageable. A single gulp of water is around, I think, a mole or a half a mole or something. So there's a lot, molecular space is this tiny, tiny, tiny little space, and we kind of have to be fully aware of that. So, okay. So why don't you give these a try? We're going to go over these in class. So let's talk about the concept of molar mass. So everything up to this point has been in with the concept of AMU in mind, individual units. Well, molar mass is going to take it a step further, and this not only tells us how many, so moles simplified the number, so it's reasonable for us to read, okay? Grams is what's gonna help us convert things to what we would use in the lab. So molar mass, the mass in grams of 1 mole of substance. So carbon 12, or carbon, we determined that has 12.01 atomic mass units. So a sample of carbon is typically going to, on average, have 12.01 atomic mass units, which is great. But we have to realize is we can't, that doesn't really mean anything to us at a large scale. So what we have scaled this up to is that 12.01 remains constant. 12.01 grams of carbon is equivalent to 1 mole, so per mole of carbon. All right, so all of the units that are on the periodic table, all of those masses, those numbers that are, all of those molar masses and atomic masses that are on a periodic table are now the unit of grams per mole. Okay, so grams per mole is going to allow us to bring the concept of moles into the real world. So we are going to start using this right now. I'm going to use the molar mass to convert from moles to grams. So what's the difference between the atomic mass or the formula mass that we did? Nothing, really. When you calculate the formula mass, instead of using AMU, you're just going to call that grams per mole. What does this actually mean? What this means is if I gather up 12.01 grams of carbon, I have 6.02. I have 1 mole of carbon. So the moles connect the idea of Avogadro's number and the number of molecules to the gram quantity, something we're going to see in these. So we just did moles to molecules on the right-hand side, the green, and now we're going to look at grams to moles, which is going to be more tangible for us, especially in the lab. So what is the molar mass of lithium oxide? So nothing changes. Essentially, you're just going to do the same exact calculation that we did for the formula mass, only instead of AMU, you're going to have grams per mole. Okay, so you should do that calculation, and I'll put the right answer here because we are going to use this number. So 29.881 grams per mole-ish. That's what you should end up with. So give that a try. That's what you should end up with. All right. Now let's take a look at this question. How many grams are in 0.85 moles of lithium oxide? So now that I had that value of 29.881 grams per mole, remember that per mole thing is the exact same as me saying 29.881 grams of lithium oxide is equal to 1 mole of lithium oxide. Okay, so that's our conversion factor. Grams per mole allows us to use that as a conversion factor. So if I have 0.85 moles of lithium oxide, I set up a conversion. I want moles of lithium oxide to cancel. And I want grams of lithium oxide to prevail. 1 mole of lithium oxide is equivalent to 29.881 grams. And now I do the math. Moles of lithium oxide cancel, and I'm left with just simply grams of lithium oxide. And my final answer is 25 point nothing grams of lithium oxide. I had 2 sig figs to start. I'm going to have 2 sig figs to end. There we go. 25 grams of lithium oxide. That's the answer. Okay. But what the good news is we now know how to measure this out. We can go to the lab. I say, oh, I need to run this reaction. I need 1 mole of lithium oxide. You're like, all right, well, I'll just go weigh out 25 grams. I've got what we need for this reaction to run. What you're going to notice is because the weight of a molecule changes, so does the quantity. So 1 mole of carbon is worth 12. 1 mole of magnesium, so same number of atoms, is twice the size though. So magnesium is 24.035, I believe. So it's a little bit bigger. So we have to recognize that mass does not equal quantity. So I can't take an equal number of carbon and hydrogen because they're different things, right? I need a different mass. I know that I'm just going to do this with a little writing. I know that for water, I need 2 hydrogens and 1 oxygen. That doesn't mean I need 2 grams of hydrogen and 1 gram of oxygen to make water, because they're not the same thing. The periodic table tells us so. They have different masses, so we have to take that into account. And that's the real thing that we need to focus on. So try the rest of these: citrate, dinitrogen tetroxide, and then the CCl4. These are multiple conversions here to go from molecules to grams or grams all the way to molecules. So next up, let's talk about percent composition, because this is also kind of a piece of it. So what is the percent oxygen in magnesium oxide? So first of all, percent composition, and we're always going to run into this whenever we're talking about concentrations or this idea, but percent of anything is always going to be the part over the whole. So the part over the whole. So in class, we could identify, it doesn't matter. So we could identify part versus whole. Okay, so if you wanted to know how much sugar is in something, if you know how much sugar is in something versus everything else, you can calculate the percentage of sugar. If you want to know, what percentage of your floor is actually clean, you'd have to measure the amount that's covered with stuff, measure the amount, and then measure the entire room, and you would know what percentage you would have. So part over the whole times 100. A percent composition is essentially the same thing. What is the atom that we're interested in? What is the mass of that atom within the compound? And then what is the total mass of the compound? So we're just going to use the individual parts to determine that. So here, what is the percent oxygen of magnesium oxide? So my magnesium oxide, so let's figure out what we have. So MgO, the magnesium part of this is 25.31. 25.31. Magnesium is 24.31 grams per mole. And my oxygen is 16.00 grams per mole. Together, the total mass, so the molar mass, think about that term for just a second, the weight of 1 mole of the compound of my magnesium oxide is equal to those two values added together. All right, so yeah, so 16 plus, yeah, so that's 40.31. Yep, 40.31 grams per mole. All right, so we have this right here is the whole. And if we want to know oxygen, this is the part. So when we're doing this math, all we're going to do, so percentage of oxygen is equal to the mass of the oxygen divided by the mass of the oxygen plus the mass of magnesium times 100. So for this one, the mass of the oxygen is 16.00 grams per mole. The total mass, I've already added them together, so 40.31 grams per mole times 100. And you end up with a total of, let's see here, 39.7% oxygen. Okay, so good. By the way, what's the percentage? What is the percentage of magnesium in this? So whenever you're doing percentages, we know it always has to add up to 100. So the quick way to do this is 100 minus 39.7, and you end up with 60.3. So percentage of magnesium is equal to 60.3% magnesium. Again, we know that because that's how percentages work, right? So 60.3% of it is going to be magnesium. So when you have one element left, because you'll notice in the next one, what is the percentage in each? You have to do 2. You could pick any ones you want, do sodium, then do phosphorus, and then everything else is going to be oxygen in the example 18. So it just adds up to 100. It should add up to 100. Good. And so do that one, try barium nitrate, and then we're going to take a look at 3.2, but I'm going to put it in the next video.